Okay, guys, let's get it started. In today's class, we will briefly discuss about a more complex discrete event simulation system by the example, and then we will discuss about your term project. Okay. Okay. In so far, we talked about how the discrete event simulation system works, right? Um, Many of them are just number crunching operation as long as we truly understand how the system works, right? This one, in previous class, we just briefly talked about the simplest possible system. A customer from a population, unlimited number of population, arrives randomly and waiting in the waiting line, which is a queue, and waiting for the service. The server provides the service, and the service time is also a random variable. And once service is done, the customer will return back to original population. So, most simple thing. In computer software, the population, such as unlimited number or something like that, is really, really hard to implement. You know, unlimited number of something, infinite something are actually conceptual thing, not a real number. So everything is just same, but except this unlimited number of population, everything is exactly same in usual software such as Delmia Quest. So instead of having the unlimited number of population, in many discrete event software, they have something called source and sink. Anyone familiar with marine hydrodynamics and the potential theory? If you'd like to do some advanced analysis, sometimes you have to have something called source and sink. You know what I mean? In source, customer generated. In sink, customer disappeared. So instead of having population, waiting line queue, and server, and going back to population, in many discrete event software, the customer is generated by the source and disappeared by the sink. The operation of the sink is really, really simple. When customer or part or whatever, the entity arrives to the sink, it just absorbs it. Whatever customer, whatever part arrives to the sink, it just disappeared at that moment. However, the only function it provides is observing or sinking and then counting the statistics. How many customers are observed and what would be their usual inter-arrival or something like that. Source. Since we are substituting this source with population, all you have to do is inter-arrival time of your customer, right? And in this model of discrete event simulation, you are free to make a multiple source and multiple sink. Okay? Okay. Here, let's look at a little bit more advanced example. A car hop restaurant, drive-in restaurant. It's very popular in United States. You don't have to get off from your car. You can just drive through to a side window and you can order it, and the food you ordered will deliver to your car. This is the kind of modern style drive-through restaurant, but in older times, there is a server. You know, you are supposed to park at the parking lot on this car hop restaurant, and there are car hops. It's just a waiter wearing roller skate and serving to your car, and you know, getting order, go to the kitchen and bring your food to your car and get the bill and pay. Everything is exactly the same. So consider a drive-in restaurant where car hops take order. Car hops are actually things like that. This is drive-in restaurant, and there are 2 cars parked here, and this lady is one car hop waitress serving. Okay. Able is better than and better than baker. That's one. Oh. Okay. Let's do this again. Inter-arrival time. You know, car are the customer in our system. Okay. Inter-arrival distribution of car, and it also randomly distributed, and this one can be defined by statistical distribution, and so it's ranging from 1 to 4, and it has its own probability, and thus cumulative probability, and summation of C, D, F should be 1, and we can randomly transform by assign this random digit to the CDF function. So in doing this way, we are transforming into uniformly generated random number into some statistical distribution following random numbers. We've talked about it, and I think everybody's are familiar with this kind of transformation, right? Okay, customers are now arrived to the waiting line, and thing is, now we have 2 servers. One is Able, the other is Baker, right? So service distribution of Able is ranging from 2 to 5 minutes, okay? And it has its own probability, cumulative probability, and things like that. Also, okay, let's go back. 2 to 4, 5. Three to 6. Okay, has different service time distribution. Okay, let's go back to the numbers. This is the simulation. Okay, thing is very similar. For the customers from 1 to 26, you know, we can generate uniformly distributed random numbers like this. And by this, we can tell that in our system, we assume that whenever the first customer automatically arrives and when the simulation starts. Okay? Any question about having this random number and getting the time between arrival, I mean the inter-arrival time? It should be based on the table we talked a little bit ago, right? Here, inter-arrival distribution of time. from 1 to 100, based on this randomly generated number, we can automatically transform this random thing into this random inter-arrival time generation. So in that way, this inter-arrival time is generated. Clock time for arrival, it's easy. The first one is automatically here, so it's a 0, and 2 means this one plus this. Same thing. It's since the definition of inter-arrival time means so nothing special. So we know when each customer arrives randomly. So this column is done like this. Okay. The next step is to generate run the random number generator once again to make service time. Okay, you know, in problem statement, when customer arrives, this customer don't know his server will be able or baker. The first available server will be his server, right? So we don't know before, right? Okay. But when both of them are at the same time available, able will be automatically the service provider, right? Okay. So random number 95. Able and Baker at the initial stage, both of them are available, and so 95 falls into here, right? So it requires about 5 minutes of service time from Able. Service time requirement is Able 5, and its service starts from the 5, so it's a 5, and service end is 5. Okay. But second customer arrives at time is 2. At that time, Able is busy, right? So it automatically assigned to the baker, and randomly generated number is 21. Baker's 21 falls into the first here, so it requires 3 minutes of time, service time, and service time begins at 2. Okay, so service ends here, right? And third customer arrives at time of 6. At 6, both of them are also available. You can do the same thing here. So based on this one, 3 minutes of Able service time is required, and at time 9, everything is done, and the next customer arrives at time 10, so both of them are also available, so Able is also, once again, the server. So 92 means 5 minutes of service time, and arrival time 10 is the beginning time, so at 15 it will be done. But next customer arrives at 12, so Able is busy at the time, so it is automatically assigned to the baker. Okay, and 89 is baker's 6 minutes, so 12 start time, 6 service time, and 18 will be the service end time. The next customer arrives at 14. At 14, also baker is busy, however, Able is busy. So, have to wait until it becomes 15. The first, it ends at 15, it ends at 18, so this one comes first, so it starts from 15. 83, 38 of random number transformed into 3 minutes of service time. So it becomes 18. And because of that, 15 minus 14 is 1 minute of the waiting time. If you do that again and again and again and again, then eventually you can run by your hands the simple parallel server discrete event simulation. Any question? Yes?
Why is always able being given the responsibility to serve? Baker is being employed when able is busy. Can it be uniform?
Oh, okay. You know, that's a very nice question. Usually, it's a natural that when there are n number of multiple server, you go to the empty server first, right? Okay, so out of n, if there is only one empty server, there is nothing to consider. But if there are more than one empty server, what would you do? You need another consideration. So this one, the first available server or the last available server and the like will be the rule kind of. And because it routes things, we call usually routing rules. Has to be very careful in defining this routing rule. There are numerous other possibilities in specifying this kind of routing rule. Okay? This is a kind of abstracted one. There is no consideration of spaces. Okay? But in real car hop restaurant, this is natural thing. If there are multiple empty servers, the shortest distance server will be usually taken. You can also specify such kind of geometrically shortest distance server first here. Or last available, the server which finishes its service time lastly can be also selected. So there could be a numerous other possibility in defining these routing rules. But for this Able Baker example, I just choose that for the simplicity purpose, whenever if both of the servers are available, then Able is the first choice to make things simpler. As you specified, we can specify a little bit complex rule, such as we can keep the log of the service time. So at this customer number 8, the service time of the Able is 5 plus 3 plus 5. It provided 13 minutes of service time already. But here, Baker only provided 9 minutes of service time. So, based on that, we can assign that if both of them are available, the shortest summation server should get the customer. We can make such kind of routing rule. It's up to you. But have to be very careful. Does that reduce the overall customer's waiting time in the system? Nobody knows. If systems, routings, and queues and servers are getting more and complex, there is no simple answer. Have to run the simulation. Okay? That's the goodness of this discrete event simulation. Think of that. This is the real factory. Okay? And your shop manager, if this is a milling machine, 5 milling machines are there, and there is one manager, and let's assume this is you. You are supposed to distribute the milling machine's job. out of waiting queue, what would be the best strategy, best rule? Things could be like this. If this is more experienced one and has the shortest service time compared to the other one. So if you assign a job here, it takes about 1 minute, but other servers will take about 5 minutes or so, which will end up giving job to the first server. Is this the best thing? I don't think so. There must be some other very nice strategy, and this discrete event simulation is really nice tool to verify if your strategy is best or not. Okay? At the same time, there is a huge downfall about this discrete event simulation. It can verify by realistically run the simulation in very short time. However, it cannot automatically generate the best possible strategy for you. You have to bring out your own routing rule. This discrete event simulation software does not provide this. It only verifies by simulating like this Microsoft Excel sheet. The core is just like this, but in the next class, our TA will teach you about Delmia Quest. It's a very nice. Everything is run in 3D virtual environment, and it can also animate things, and it can turn around the world and see whatever angle you want to see the system. But that's just the eye candy. You know what eye candy means? Eye candy. A sweet thing only for your eyes. Inside of it, same thing here. The result is exactly the same like this. But there is some goodness when you do the things in 3D simulation. You know, in this one, we cannot think about the dimension and their collision or things like that here in this kind of world. But if you do the 3D, everything can be done. You know, if your lane is this much, I don't know, in real shipyard, because they are building huge blocks and they transport it, sometimes it is very big deal. If our block can squeeze out this narrow road or access route, we cannot do it here, but when we use 3D, you can check it, really. Okay, there is a, but also, it's a easier, but in 3D is nice, but somebody has to construct the 3D geometry. So it requires a lot of work to run the 3D simulation. So, up to you. Okay, question about this simulation? So, my question is, if I give some kind of system diagram, and can you make your own simulation in this form for about 5 or 10 customers in final exam? Why not? Lack of time? Don't worry about it. You will have enough of time. Okay? Has to clearly understand how this table is working. That's the key essence of how this discrete event system is working.
So you will provide us with the random GPs.
Yeah, random digit. Because if I ask you to run your calculator to make the random one, it's awfully difficult for me to grade it. Okay? The answer should be exactly same among you. for me, the grade. Okay. Here, what would be the system state of this kind of discrete event system, discrete event simulation model? System state. With what parameter can you describe this system state? Well,
service time of table and baker. The service time of table and baker.
Service time? Yep. Is it empty or working? Is it empty or working? Two parameter and the number of customer waiting in this waiting line. If you have this 3-1, then you know the whole system, right? Am I right? Yeah. There is a kind of interrelationship among this variable, because if this one is empty, if any one of these two server are empty, then the number of waiting customers should be 0, right? If some of them are empty but somebody is waiting, that does not make any sense for this kind of system. There are such kind of relationship. However, if we know Abel is busy or not, Baker is busy or not, and how many customers inside of this, then we can kind of reconstruct the picture taken state of this system, right? Okay. So LQ, length of the queue, the customer inside of this waiting line, and Abel's is busy or Baker's is busy. Okay? By filling out this kind of form, you can reconstruct this simulation table. Okay? Okay. System state 3. Customer here and busy or not, busy or not. Okay. Entities representing customer CI who arrives at time. Is it necessary, or can we do the simulation without the definition of this entity? It's up to you. For example, if you'd like to distinguish customer, for example, by running this kind of simulation, and one of the question you'd like to answer throughout this simulation is something like that. What is the average service time of the customer who served by Abel? Okay? Or who served by Baker? In order to answer those kind of questions, we have to think of that Microsoft Excel sheet. Out of it, if you'd like to get the statistics of the customer who served by Abel only, then we have to distinguish customer served by Abel and served by Baker. And list them up and do the summation and divide it by the total number. By doing that, we can only answer the average service time served by Able or served by Baker. If we'd like to answer such kind of question, we have to distinguish customers who served by Able or served by Baker. Only then we need this kind of entity. Customer C1 served by Able, customer C2 served by Able, C3 served by Baker. So, but if we are not interested at all about this kind of question, we are only interested in the average service time of the customer, average waiting time of the customer, then we don't need this kind of entity definition. Okay? Do you know the... Okay. Okay, at this point, the number of system states are 3. In previous class, the number of system states were 2. Because we are only thinking about one queue, one server. So busy or not, and number of waiting customer, 2. But here, busy or not, number of customers. We have to know 3 system states variable. Because of that, we need, except this stopping event, we need 3 events. Event is some occurrence that changes the system state. Okay? And it's best defined by there is no coupling. You know, do you know about the axiomatic design or thing? Coupling is bad and okay. Things like that. Arrival event. Let's assume A happens. And out of the 3 system states, what is changed? Yeah. Basically this. And it does not affect the other directly. There is a service completion by Able, DA, departure at A. If DA happens, this system variable are directly affected, and this is the only system variable that directly affected. Okay? Service completion by Baker, DB, here. So there could be, there are 1-to-1 matching of system variable, system state and events. This is well-designed discrete event simulation. If there is a coupled thing, then it's awfully hard to make the numerical simulation. Coupling is really, really important. When things are getting larger and larger and getting complex and complex, there is no control. Okay, let me give you a very nice example of coupled design. It's not discrete event simulation thing, but I saw this from some of the book. There is a refrigerator. You know what the refrigerator means? You put things in to store it in a cool temperature. And there is a 2 dial gauge. This is the controller. Okay? And usually refrigerator, freezer and refrigerator, you know, the things for the ice and things for the groceries. And for a very old design refrigerator, freezer, there is only 2 control knobs. And you know, in our own straightforward mind, this one should be temperature gauge of this room, and this one should be temperature gauge of this room, right? It's just straightforward. In user's viewpoint, it is decoupled controller, right? Whenever our needs change, we can easily adjust it, okay? But in older times, those kind of control thing was not so common, so people made this kind of controller. Let's call this is A and B. There was this system. You know, cooler is the source of the actually cooling thing. And this blower, so switch A means the temperature of the cooler. Switch B controls the portion of how much percent of the cooled air will go to this side and how much portion of goes to this side. And you know, using this, it is awfully hard to directly control your temperature intuitively. It's a bad example. One very good example of bad coupled design. Okay, you know what I mean? For example, if this is the system, what would you do? If you do decrease the temperature here, but let the temperature in this room just the same, you have to control both things at the same time. Very, very bad coupled design. But anyway, okay. In Carhub restaurant, event notices should come like this. You know, any question about this events, type of events? We have this A, DA, DB event here. And based on this event, we got to have event notice. What kind of event will happen and when? Okay? Sorry, the thing is broken here. So A event. So this one represents that arrival events will happen at T, and the entity which arrives is a C. So A, comma, so based on here, first customer will arrive at time 0 and customer 1. Second customer will arrive at time 2, customer 2. Can you construct this arrival event based on this? Okay. DA, same thing. Here, DA. Based on this Microsoft Excel, we know that DA will happen at time 5, customer 1. And DA will happen at time 9, customer 3, and the like. Same thing. DB will happen in time 5, customer 2. Right? This is the event notice. So internally, the system keeps generating the events notice based on this inter-arrival time random distribution and service time random distribution. Okay. And we already discussed about what is the definition of delay. Okay. And this is the table. Thing is like this. Based on this based on the system, it is not actually create this Microsoft Excel sheet kind of simulation chart at the beginning. It actually creates near future events and events notice. For example, if we run this Abel and Baker simulation for about 1,000 hours, then it only generates about 1 or 2 hours of events at that time. It generated, and this is the generated event notice. And they put this notice into the future event list. List is a big array, and it is automatically sorted. So, for example, if you initially generate this kind of event list and put the thing in the future event list, this one should come first because time is the earliest, and this one, and this one, and then. So inside of the simulation system, future event lists are just kept there, and whenever the new events are inserted, it is automatically sorted. Okay? And then the first one, which is the nearest future one, is popped out, which means that event is just happened. This is event notice, not the event. You see the difference between event notice and event. So event notice. So in the queue, this is here. This one be here. This is future event list. Okay, current clock at time 0. At time 0, in future event list, first one will pop out, which means at that time, at time 0, this number 1 event just happened. Okay, so it is destroyed from our future event list. Okay, and based on, do you remember the flow chart? We've talked about this. Whenever events happens, the system automatically search, are there any related future event notice? And if there is, put that future event list into this one automatically. Okay? Okay, at time 0, thing is done. And system state accordingly change it. And done. The next thing the next thing that this future event list will do is time advance. Thing is, the nearest event will be number 2, and it happens at time 2. Okay, because of that, the simulation clock don't have to count every time or minute between this 0 and 2. It just goes to the next time step, which is 2. Time advance. This is the key feature. Since we are doing like this, that's what we call discrete event simulation. And now the next nearest future event is executed and popped out, and popped out. And it could be possible that new event notice are plugged into the here, but the newly come event could become somewhere between them, because it's automatically sorted based on this time. Whatever it is, the next one will be time advanced, and it keeps doing and doing until it reaches this event, end of the simulation event. It's a key element of this discrete event simulation system. Okay, it explains, this slide explains that system state, a list, future event list of all activities currently in progress and when each such activity will end, and status of the all entity and current membership of all these, plus current value of cumulative statistics and other things, which is basically what we explained throughout this Abel and Baker and single server, single queue simulation system. Okay, question about this discrete event simulation. In Wednesday class, TA will teach about the Daniel quest, and I strongly recommend you to do the simulation based on these two examples. One is the single queue, single server. The other one is single queue, two server. And that's it. Once I check the real data. Okay, about the team project. It's a realistic problem. So you have to have some, you have to use some kind of your engineering knowledge. You have to simplify if something is negligible, or, well, anyway, just assume that you're a professional layout designer, and the factory config codes factories are your customer. You have to persuade that your solution, which will be your product, your solution is very much attractive to config codes executives. That's it. Okay, based on that problem statement, I think you have the list of the department and their required size, and there is nothing like their relationship, right? Which department should be close to the other department, or which other department should be very far from the other department. There is no such information given to them. All you have to have is the flow, volume of flow among the department. And since this is the real problem, those flow are not straightforward. Something is, if this is the flow, then this is the flow, and there is many other things like that. Things is like that in real world. So have to have some practical assumption. Okay? And based on that, construct the flow F sub I and J. Okay? Once you do that, then your next step will be the construction of space relationship diagram. Okay? And there is a little complexity because there are mezzanine, and some department should be assigned to mezzanine, and some of the department are not arrangeable to the mezzanine, right? So think of this mezzanine as another space. Okay? Question? I think you don't have enough time to write your computer software or some optimization tools. So I strongly recommend you to just do it everything manually. I think, you know, if you can draw the grids and you can justify things and you can basically calculate using your calculator. So it is doable manually. But in order to actually find the global optimum, the optimum layout design, you have to check many number of layout alternatives. While doing it manually, the number of alternative evaluation will be very much limited. However, other than that, I don't think we have the other choice. So do it manually and search for several other type of layout alternative and choose the best possible layout among them. You know, using computer software, you can evaluate hundreds or thousands of layout alternative automatically, but I don't think we have enough time to construct the computer code to do that. Okay? So I strongly recommend you to work together to construct f sub I and j, okay, and build some kind of strategy. How do you model things? How do you model the constraints, such as this department cannot be located on mezzanine, something like that. So once you arrive at the consensus level, I mean the agreed on the generic strategy, then we are 6 people here. So based on one space relationship diagram, 6 of you make 6 other design alternative and evaluate, you know, the cost of the layout and choose best one among it. I think that's the kind of practical approach at this time. Okay, question about doing the project? Any other question? No? It would be very, very nice of you if you still construct a computer code to optimize the layout. But yeah. Any question or doing the team project? Okay, have you discussed about the problem? Or have you ever had a meeting today after the class? Okay, good luck. Okay, this is the end of my course today. I have nothing more to talk about it. So let's call it a day at this point and have the team project meeting. Okay? If you have any question, keep bugging Bongun, PA. He knows everything. Okay, thank you.